Right. So we need 0, 1, 2, 3, 4, 5, which is 6 different states, and however many states you have to get that from a power of 2. So with one flip flop, you can have 2 states. With 2 flip flops, you can have 2 squared, or 4. With 3 flip flops, you can have 2 to the third, or 8. Well, 4 is not enough. 8's too many. You don't have to use them all, but um, but you could do that. Okay. Um, did he say that your exam um, covers just the stuff since the midterm, or does it cover
Everything.
covers everything?
Yeah.
Covers everything. Okay. So for this next one, I have. So this would be from earlier in this semester. We want to build this function using a 4x1 multiplexer. Okay, so here's my pen. All right, so what does a 4x1 multiplexer do?
It has a switch with 4 inputs.
All right, so y'all did several labs with these. So what a 4-to-1 multiplexer does is it has 4 inputs, 0, 0, 0, 1, 1, 0, 1, 1, and it has 2 select inputs, S1 and S0, that tell you which one to choose. And whatever the value of S1 and S0 is, you take the value that's coming in to that input on the multiplexer. So the way to do this is to do a truth table. So we have A, B, and C. How many possible combinations are there of ones and zeros for A, B, and C? Boy, y'all are really working hard today.
8.
8? Now, don't make me go back and change. I emailed Dr. Trahan and told him how, I seriously did, told him how great this semester's class was, that I was really impressed. And so participate. All right, so what does it mean that this equals the sum of the min terms 1, 2, 3, and 6?
Let me be honest, I completely forgot how to do this.
Okay, that's okay. Anybody else remember, have any ideas besides James? Because he has been answering, which I appreciate very much, and I'll have to come back to you because no one else will answer. But anyone else want to try?
I believe this is all of the inputs that are listed and are based like 0, 0, 0, 0, 0, 1 is going to be a 1 and every same for so row
Yeah,
row
you
1,
row it.
row 2, row 3, row 6 is going to be 1, everything else is going to be 0.
You got it. Thank you. All right. So we have you know that the min terms are labeled 0, 1, 2, 3, 4, 5, 6, 7, and that also equals their value in binary. And the rows that are equal to 1, 2, 3, and 6, they have a 1 in them. 1, 2, 3, and 6, and the others all have 0.
I have a question.
Yes.
Why are the first 4 in A 0, and then the next 4 is 1, and then B is different, and then C is different? Did you go over that? And I was just not paying attention.
These are the numbers, the binary numbers 0, 0, 0,
Oh, I
0,
see.
0, 1,
Okay.
0, 1,
I was
0.
looking at it.
Yeah. You were looking at it because I wrote it funny, because that's my shortcut way of writing it.
Okay.
So if I have, it's just my quick way of writing it, is if I have 8, if it's going to be 8, it's 4 zeros, 4 ones, 2 zeros, 2 ones, 2 zeros, 2 ones, and so forth. It's just a shortcut.
I got it.
Okay, So we want to look at our rows here and see if we can figure out if there's anything that we can do to make this, because we have 8 possibilities over here, but only 4 inputs over here. So we want to look at our table here and see if we see any patterns here. So, for instance, I might notice that if, let's see, um, if I have, so what I want to do now is compare these. No, I just want to look for a pattern. So let me see if I see any patterns. Let's think about just looking at A and B. Do we see any patterns for A and B?
If we cut out C, there, every second, every 2 rows is the same. Contents. So like 0 and
So
1
yeah,
have
0,
0, 0,
0, 0,
0,
0,
0.
0, 1, 0, 1, 1, 0, 1, 0, 1, 1, 1, 1.
I'm sure y'all have found something, but I guess I'm not entirely sure what it is, but I think you're.
Like every two rows in A B are exactly the same. So it's like
Oh,
the
yes,
first two
right.
are 0, 0, 0, 0,
That,
and
right, that's
the other
right,
two is
that's
0,
right.
0, 0.
So if we look at that, so if, so what you can do is you can say that A, B together make 0 for those 2 rows, 1 for those 2 rows, 2 for those 2 rows, and 3 for those 2 rows. And that is exactly what you want to do. And I'm glad that y'all discovered that rather than my just saying it, because now you see where it came from. Because when we did this in a lab, nobody saw where it was coming from. But now you see that it's because every 2 rows of A and B are the same. And so I'm going to use these values for my select. So this is going to be S1, S0. So I want to see if S1, S0 is 0, then my output, so I'm looking at S1, S0 is 0, my output, if you look at my output, it's identical to C, right?
Yes.
Yeah, and so I can just say C is my input for 0, 0. If y'all remember doing this in the lab, pretty much every input is either going to be 0, 1, C, or not C, because those are the only possibilities we have. So now, if I look at where AB equals 1, what do I want my input to be? 1. And now if I look at where AB equals 2, what do I want my input to be?
0. Oh, yeah.
0. And when AB equals 3,
Not C.
not C. And so what that means is my select inputs up here are A and B. And if my number is S1, S0, and I want these to be A and B, then I want A to be S1 and B to be S0.
I don't think it's that one.
Yeah, I thought the, like, as it was, yeah. I'm just wondering, I thought y'all had to go like this, or is that just like graphical convention? Doesn't
Usually
Splitting
when
the
we test them on this,
groups of
it
2
just makes it easier.
and you're
It's
Making it 0, 1, 2, and 3.
Because A, B are the same.
Okay.
They're both 0.
Okay.
And they mean 0. So I'm calling together, I'm saying AB is 0. And then the second two rows, it's 1.
I see it now.
Yep.
And you only group them together because it's equal.
I group them together because this is how you do this kind of problem.
I get it now. Okay.
Or this is an easy way to do this kind of problem. If your multiplexer has half the number of inputs as your truth table, you do it like this. You take your all of your variables except 1, and you make those your inputs, and then what you're going to get on the last column is either going to be 0, 1, that last variable, or not that last variable.
For one and 0, like where it says that 1 is equal to 1 and it says that 2 is equal to 0. Does it matter what C is?
It does not.
It does
We're
just only looking at the purple portion.
Right, because the output here, F,
Yeah.
when AB is 1, so A is 0, B is 1, the output is 1 regardless of what C is.
Right. Okay.
Does anybody remember the lab that I'm talking about?
Yes.
Anybody else? Yeah.
I do, sort of,
Sort of? Okay.
So.
felt like a lifetime ago.
It was.
So whatever C is, whatever D is. So this, for both of them, one, so you can put it on the screen. And then, well, we mix up, we might come to C next week.
Okay, so
This is not.
is everybody ready to go on? All right.
That output was given.
Based on the below state diagram having input X and output Y, input X and output Y, it's hard to read these, and so I'm assuming the way this is drawn is that the input is the first bit and the output is the second bit. So it must be that 1, 0, like if you see a 1, 0, that means the input is 1 and the output is 0. Let's see if that makes sense. Yeah, it does make sense. Okay, so it's drawn that they don't have the little slash in there. All right, so given that, which of these, looking at this state diagram, which of these statements is going to be true? When X equals 1, the state B will remain unchanged and Y equals 0. That certainly is true. Are the others all false? All right. Does anybody have a question on that? Anybody not see that?
I don't see it.
Okay, so let's just go through and look at them. It says when X equals 0, the state B will change to C. So I'm going to go to state B. When X equals 0, that's going to go down. It says B will change to C. That's correct. And Y equals 1. Nope, Y equals 0. So that's not true. When X equals 0, the state C will change to D. When X equals 0, nope, C changes to A. So that's wrong. When X equals 1, the state A will change to B. So when X equals 1, A changes to B. That's good. And Y equals 1. Nope, Y equals 0.
Okay, I see it.
Okay. Okay, I'll go ahead and do it because one more person had a question. So when X equals 1, the state B will remain unchanged. Here we go. Yep. And Y equals 0. Yes, because that's what the second part says. Any other questions on that one? All right. a sequential circuit with two D flip-flops A and B, one input X and one output Y, is specified by two input equations and one output equation. Draw the logic diagram of the circuit, draw the state table, derive the state diagram. So let's do that. Okay, so we have two flip-flops labeled A and B, and they are D flip-flops. And our output Y is A or B. And our input into A is X and A not. So I will take so X and A, and our input into B is not A and B.
You still have 22.
No, I had Duncan.
Is he better?
He's much more good. He's like insane. It's like I never took a computer science class again. It was ridiculous. But good. I mean, I like the class. It's just it's gonna be more. I had to take
Okay, so for our values for A, B, and X, so how many states are we going to have in our state diagram? 4. And how'd you come up with 4?
A, B, X, Y.
It's just A and B. So the number of flip-flops tells you the number of states. So we have 2 flip-flops, so it'll be 2 to the second. But it's not immediately obvious what our states are going to be, because we know that Y depends on A and B also depend on X. So let's just go ahead and set up a little truth table here. And from this we can figure out what the output of what the next state will be for A and what the next state will be for B. Not the next state, but the next output for that one. So DA is X and A knotted. So that would be 1, 1, 1, 1, 1, 0, 1, 0. And DB is the not of A ANDed with B. So that's going to be 0, 0, 1, 1, and the rest will be zeros. And Y is the OR of A and B. So this DA and DB, that's going to be what the next state is. That's where we're going to get the next state from. So AB, this will be the OR of A and B. So 0, 0, 0, 0, 1, 1, 1, 1, 1, 1, 2, 3, 4, 5, 6. It should be 1 all the way down. Only the first two would be 0. All right, so let's see if we can draw a state diagram from this. It might be easier to do a state table first. So if I said there were 4 states, what do you think would be a reasonable thing to call those 4 states? All right. Oh, okay, we can do that, but I'm thinking we can call them. Yeah, so next, x equals 0. Let me make this neater. So how did we come up with the idea that we were going to have 4 states? The 2 flip-flops. Those define the states. What are the possible outputs? What are the possible outputs of flip-flop A? A and A prime, and so 1 and 0. And what are the possible outputs for B? Same thing. So it makes sense, I think, to think of these as A and B, and 0, 0, 0, 1, 1, 0, 1, 1, that will look at our current state being 0, 0, and then what our next state is would be DA, DB, DA, DB, for x equals 0 and x equals 1. Now, is this Mealy or Moore?
Moore.
Who thinks Mealy?
I don't think anything.
Who thinks Moore? Who's waiting to see what other people do? Okay, you're right, and I have cookies in my office, and you're getting cookies. Yeah.
Did you say million?
Yeah, that's a more.
It's more. It's more. How do I know it's more? What does y equal? How is y
This is
defined?
the next state, so if your x is
So-
defined only by now.
Y is defined by A and B only. And what are A and B? A and B are how we're defining our states. It's y doesn't have x in it at all. So if you look at the problem, y equals A or B. And our states are defined by just A and B. And so our state will tell us the value of y. So if A or B is 1, our output will be 1. So this is a Moore machine. It does not depend on the input. Okay, so here's our output. This is y. And we know the output is equal to A or B. So our output is going to be 0, 1, 1, 1. And if you go back and check and you look at your table, that ought to work. Okay, so now we're going to figure out what the next state is if x equals 0 and A and B equals 0, then dA is 1 and dB is 0. And if x equals 1, we also get 1, 0. So I'm just looking at my truth table. Now if AB is 0, 1, and x is 0, I get 1, 1. And if AB is 0, 1, and x is 1, I also get 1, 1. If AB is 1, 0, and x is 0, I get 1, 0. And if AB is 1, 0, and x is 1, I get 0, 0. And if AB is 1, 1, and x is 0, I get 1, 0. And if AB is 1, 1, and x is 1, I get 0, 0. Make sure that matches what I have here. I don't know, I don't have it drawn right.
Is there any point that x, the value of x, would prevent a from becoming a certain value in the same row?
No. I mean, if x can't, no. You can fill in every row in the table, even if so are you saying could there be such a circuit where that would happen?
I'm saying in this case, or really, I guess in any case, but a simple one like this, that would be on the test, right?
Right.
Uh,
There could be something incompletely specified. There could be a don't care.
okay.
Okay, so that is a possibility, and this one it doesn't happen that way. So you still have to fill in, every possible state. You know how when we do a state diagram, we put all the states in, and then if one is not used, we put in don't cares. So in this problem, that did not happen. But it could, and that was a very reasonable question, in which case you would just put don't cares in. Okay, so now we need to see if we can draw, we have our state table, now we're going to do our state diagram. So we have 4 states. Zero, 0, 0, 1, 1, 0, and 1, 1. And we can write our output on the state itself because it's a Moore machine. So I think this one was 0 and the others were 1. And state 0, 0 always went to state 1, 0. Zip. So you don't have to put anything on that because that's it. I'm on part C of 5. Part C of 5.
You said, I'm sorry, could you explain that line one more time?
What I just drew?
Yeah.
Yeah. So from state 0, I go to state 1, 0 regardless of what x is. I could draw a line for 1 and a line for 0, but that's too much work. Okay.
And is it already known that if you just draw one line, it's okay?
Yep.
So the same for the next one?
The same for the next one. 0, 1 goes to 1, 1. And then 1, 0, that's different. 1, 0 goes to 1, 0 when x is 0. And 1, 0 goes to 0, 0 when x is 1. And 1, 1 goes to 1, 0 when x is 0. and 1, 1 goes to 0, 0 when x is 1. So that is our state diagram. Yeah, I'll get, hold on just a second. I want to see if this particular. Huh. So the person who made this question on the test didn't realize it was a Moore machine. Okay,
Oh,
yes.
so I know it's already said right here is DA and DB what they are.
Mhm.
But can we derive the Carnot map?
Sure.
Or using the Carnot map from the state assigned table?
Yeah, if you wanted to go backwards,
Yeah,
yes,
backwards,
you
yeah.
certainly could, yes,
Okay.
yeah.
And you would just take you would take the two DAs and take the lines and put them or just put them across each other.
Yeah, and we're actually gonna do one of
Okay,
those
okay.
later, yeah.
I was
It's not, it's set up a little differently, but if you don't understand how to come back to this one with it, I'll
Okay.
do that, yeah.
I'm a bit confused. I thought that because X, with the input of X would change which states you would get.
It did,
Well, as in, well, wait. But if, wait 1 second. I thought you would get a different Y value depending on the X input.
okay, that's the whole Mealy-Moore thing. So, of course, X does change the state, but it changes the state on the next clock cycle. And so it's just like the state does, when I first heard this, I'm like, what do you mean the output doesn't depend on the input? The state clearly depends on the input. Yes, but the output doesn't directly depend on X. It's not in the output equation.
Alright, yeah, I see my issue now. Yeah, I wasn't thinking about how DA, DB weren't the inputs into Y, and so that messed up all the work I did.
That's right, yeah. Yeah, so it's A that's the input and not the next one. And so it's like the X did its work on the step before, and all you need to know the output is what state you're in. Okay, any other questions on this one? And if not, I'm gonna stop this recording and move on to the other computer.